Thank you all. And thank you to Alex and the others for organizing this conference. So several people have been beating up on pandemic modeling in previous talks. I will be joining their number in an effort at balance. I'll also be trying to sort of give an example of good practice, if you like. And what I'll be trying to do is to relate good and bad practice to the underlying metaphysical situation of what we're trying to study. So imagine two different kinds of worlds. Here's the first kind of world, what we might call a stable world. In this world, happily, causal relations are stable and reliable across many different cases. Other kinds of relations are as well. How best to investigate such a world? Well, it naturally calls for a master model, a model that captures these reliable, wide-ranging relations, causal relations and others. Paradigm case of this would be a Newtonian model of gravity, simple inverse square model of two bodies gravitationally attracted to each other. We can apply the same model to all cases of massive objects. Why? Because the force of gravity, we have good reason to think, is very stable. It applies the same way across the whole universe. It's a universal law, it's an extreme case. We apply the same model, we just change the parameter values for any particular application, the particular motions and masses of the bodies involved. So that's the first case. Now let's take a diametrically opposite case. Let's call it fragile world, world number 2, if you like. And in this case, causal relations are quite the opposite. They're not stable. They're very fragile. They're intermittent. They're often fleeting. It's very unpredictable when they're going to apply and when they're not going to apply. They're unreliable beasts now. Now, if we're studying a world like this, then the strategy of developing a single master model is no longer an efficient or an effective one. Why? Because just having a model of one lot of stable relation, one lot of relations, those relations only apply unpredictably. Rather, to understand any particular situation, we're going to be forced each time into idiosyncratic local detail. If there are no eternal laws that apply always and everywhere reliably, every time we're going to have to take a new look at the details of the case. We might have many different models that potentially apply, and we want to know which of these models applies in any one situation. So instead of the single master model strategy, we're forced, or we ought to be forced, towards a much more contextual strategy. Life is more difficult, if you like. We don't have a single Newtonian model that's going to be helpful always and everywhere. So the next question, of course, is which kind of world is the epidemiological world? In brief, it's a mixture of the two. There's stabilities and fragilities everywhere, but very often fragility is going to be the feature of the kind of the relations that we're interested in. And that will be the case in my two examples today. So as I say, I'll be looking at two examples, one bad and one good. Brief moment of self-advertising. This sort of metaphysical underpinning to good methodology is a book project of mine, which I'm writing at the moment, called Science for a Fragile World. Okay, so if I can actually, there. Technical hitch, here we go, right. Let's start with the model that lots of people have been beating up on, and that's the famous one now in this conference by Neil Ferguson and colleagues at Imperial College from March 2020. And it was this model famously that persuaded the UK government to impose a national lockdown due to a series of dire projections if the government did not do that. Now, what's the problem with this Ferguson model? The biggest problem is its lack of empirical validation. It has no track record of accurate predictions. The prediction versus projection distinction is important, but when conditions more or less match the base conditions of a particular projection, what the model says would happen is often far variance what actually did happen. The model itself was adapted from originally an influenza model, as many of you will know, and it lacks accurate predictions in its other applications as well. It's not just COVID. That's first problem. Second problem, the model makes many inaccurate assumptions. In fact, frequently it just makes educated guesses for parameter values. I list a few there. Yet another problem is that many relevant factors and relations are omitted from the model, often by its own admission. Now, having inaccurate assumptions or omitted factors does not necessarily a terminal blow. If the model makes accurate predictions anyway, then we can forgive these idealizations. Or perhaps one might run sensitivity analyses to show that the exact estimation for different parameters doesn't matter that much to the predictions. But neither of these get out clauses apply here. There are no accurate predictions, and there's only very limited sensitivity analyses that are quite inadequate to make us trust the model. All in all, I claim, according to no theory of scientific explanation, does such a model explain. In fact, I think we should put 0 epistemic weight on the Ferguson model whatsoever. What's the underlying cause of this problem? The underlying cause, in my opinion, is that the modeling strategy behind the Ferguson model is misconceived. It's a sort of adapted to a sort of stability world where Newtonian type one-size-fits-all master models are a very efficient way to go. But if the target is not a stable world, then it's not a good modeling strategy. And I don't think the target is a stable world in the relevant way here. Many key causal relations here are fragile, not stable. In other words, they vary and they apply only unreliably across cases, both in different pandemics. So influenza pandemics is different from COVID pandemics and so forth. And also even within the COVID pandemic, different countries, different times of the year, different stages of the pandemic and so forth. All of these lead to big variations in the very nature of the causal relations that the model is trying to pick up, not just in the parameterizations of it. I list a few examples on the slide: the impact of border controls, determinants of the R number, the relevance of super spreader events to understanding transmission, the impact of school closures and so forth. All of these things, as some other talks have pointed out, are varying greatly between countries and so forth. So a single model that commits itself to one particular set of causal relations, it's inevitable, I think, that if the target is not stable causal relations, then a model that assumes that the causal relations are stable is bound to come unstuck. And that's what happened with the Ferguson model. The master model strategy is meant to be efficient. It's meant to be a shortcut to predictions and explanations in many different applications. That's why having a Newtonian model of gravity is such a wonderful thing. We can apply it all over the place, and it's incredibly useful. We don't have to work things out from scratch each time. We don't have to wonder each time which model of gravity applies. There's only one gravity always and everywhere. But that sort of efficiency gain is just what we do not get in the Ferguson case, as I've been explaining. It's as if the inverse square law of gravity itself varies. Sometimes it's inverse cubed, sometimes it's x to the 3/2, whatever it might be. And whatever it is, it only applies unreliably. Sometimes it applies here and then it doesn't apply over there. If that was a case of gravity, the Newtonian model approach would not be the way we'd want to go. And the same seems to be true with epidemiology. Okay, so that's the bad side, as it were. Now let's look at the good side. If the master model strategy doesn't work, then what other strategy can we use that might work? So my second example by the same people, the Imperial College Center, and indeed many of the same authors. The lead author is different, is Eric Volz, but one of the co-authors of the good paper is old Neil again. Neil Ferguson turns up, and indeed Eric Volz himself was one of the authors of the Ferguson paper just in criticizing. So in fact, there's many of the very same people, in my opinion, producing both good work and bad work. So my criticisms, whatever else they might be, are not ad hominem, I don't think. Now, what did this Volz paper from December 2020 do? This is notable because it was the first paper to identify and estimate the greater transmissibility of the so-called British variant, B117 variant. And this is obviously a very seminal piece of information as a British variant spread to many other countries. Now, I don't have time to go into the details of the paper, but if you do, you'll see that this paper is much more data-driven. It's a very different kind of paper to what the Ferguson model was. It picks and chooses a few simple models applying here and there and justifies the choice of these models. There's good reason to think that the assumptions are realistic in these cases. And as a result, its conclusions are much more convincing. They make a very strong case for the greater transmissibility of the British variant, and they quantify that greater transmissibility, adding between 0.4 and 0.7 to the R number, to be precise. I'd also like to mention, I think there's continuity between the sort of contextual approach exemplified by the Volz paper and what one might call more informal methods. I have in mind things like cross-country comparisons, where we're not doing sort of RCTs or statistical regressions because things are far too variable to make those useful methods. Rather, we're sort of trying our best to sort of uncover the thicket of confounders. Every country is a different combination of different factors. Can we sort of learn nevertheless something by comparing the experience in these different countries? For example, how effective are border controls? That varies a lot case by case, but we can still find out principles of best practice and when they're useful and when they're not useful, and so on and so forth. This is exactly what governments have done. Now, these informal methods, although they're informal and so therefore have less internal validity, they're less rigorous, if you like, than running an RCT or something. That doesn't mean they're hopeless. They can still be rigorous to an extent, and they can still be quantitative to an extent. And I would see the sort of Volz paper, which is not informal, that's very much a formal paper, and these more informal methods as being on a sort of continuity. And there's on a sort of spectrum, if you like. These informal methods effectively are using models. They're using causal hypotheses, which are causal models of a sort. And the key thing that connects the Volz paper and these informal methods is this contextualist approach. They're not trying to get a one-size-fits-all master model. Rather, they're looking very closely at, of all the many different things that are varying, what's the exact state of play in a particular case. Now then, here we go. Now there's a drawback to this contextual approach, and it's the reason why if you have stability, you don't go contextual. And the drawback is that your results of a contextual model are contextual. In other words, they do not generalize easily. So for example, the greater transmissibility of the British variant, so-called British variant, that result might not extrapolate. It was calculated from data all taken from England between October and December 2020. It does a very good job of showing that B117 was more transmissible by a certain amount in that context with that particular state of lockdown in England. Does that mean B117 will have the same transmissibility advantage in other countries with different kinds of social distancing going on at different stages of the pandemic? One cannot be sure. One needs to reassess each time. It's a solid building block, the Volz paper, and one hope it will inform assessments of the British variant's greater transmissibility in new contexts, but you can't take it for granted it will extrapolate. It's because you can't take it for granted that it will extrapolate that it's a sort of second best method. We'd love to have a single master model like the Newtonian gravity that applies everywhere. But the fact we can't is not because we're stupid or doing the wrong method. As it were, the problem is nature's fault, not our fault. If target relations are fragile, then the Newtonian master model type methods are just inappropriate. You'll end up in Ferguson land and getting nowhere. Our methods must adapt, even if it's the sort of second best contextual approach. Okay, final slide. So to sum up, methods are determined by the metaphysical nature of our target. If our target relations are fragile, then this emphasizes methods that are empirical, that are contextual, that are always working from a range of models, trying to decide which model, which causal hypothesis applies best to the particular case at hand. And it de-emphasizes the sort of master model strategy, which is more suitable to a stable world of one size fits all abstract model development. Just as a final remark, these considerations have practical import. And again, many other talks have brought up this aspect. To give one example, SAGE, the official scientific advisory body to the UK government, at the beginning of the pandemic was arguably top heavy with mathematical modelers, very much bottom heavy in the sense of having no empirical field scientists whatsoever. There was very much a sort of slant in the kinds of expertise that was making up the committee. And it's been argued, and one would need a thorough historical study to make good on this claim, but there's certainly suggestions that as a result of this, there was an initial neglect in the SAGE's considerations of on-the-ground experience, both from other countries and from practitioners at home. There was a neglect of what I called informal methods a couple of slides ago. And this neglect had consequences. Arguably, it slowed the provision of protective equipment to health workers in the UK, and it slowed the setting up of a good testing system as well. So methodology matters. Thank you all.